Hi guys, in this video, I would like to talk the sync with enthalpy. As I described before, internal energy is not appropriate for the discussion about reactivity. Instead of that, we use enthalpy in order to understand what is enthalpy. This is the important question. How can we describe the state A in PV diagram? This is PV diagram, and this is state A. P means the pressure, and V means the volume. And this is one of the energetic state as A, which can easily change to the energetic state B by changing the volume and pressure. And then the energetic state B can easily change to the state A by changing the volume and pressure. So this is a kind of round trip from A to B to A again, okay? And here you can see the area, This area shows the net work done to the system. So, do you remember that the change of internal energy can calculate it by Q minus W. Q means the heat energy and W means the work. In this case, done to the system. In that case, we can write down the minus here. So internal energy change is actually zero because this is a round trip. Then Q should be equal to W. And in this case, the change of heat content of the system equal to Q, even though the change of internal energy equal to zero. Okay. As I described before, U is not appropriate for describing the energetic state of the system. Instead of the internal energy, we can use enthalpy, large H. The enthalpy equal to internal energy plus PV. This is the definition of the entropy in the PV diagram, okay? And by the use of this definition, delta H, I mean the change of enthalpy equal to change of internal energy plus change of PV. Change of enthalpy can be described by Q minus W, and W part can be described by P delta V. Then this part, I mean the minus P delta V plus delta PV can cancel out when delta PV equal to P delta V. Under constant pressure, actually this equation is true. That means this part can be removed from this equation. Then we can obtain this equation, delta H equal Q. Importantly, under constant pressure, this equation always true. And then delta Q is delta H is change of the heat content of the system. Okay, this is very important idea to understand the enthalpy, and maybe you can understand why enthalpy is very useful. You can access the value of enthalpy by observe the change of the heat contents. And importantly, under constant pressure is under usual reaction conditions. Okay? And sometimes the internal energy and enthalpy makes you confusing. So I would like to explain another point of view to understand enthalpy. If you think about the danger of the bomb, you need to think about the power of the bomb and potential energy of the bomb. This is a kind of PV diagram of the bomb. This is the bomb on the ground, low height. It's not so dangerous. But once this bomb was carrying up by airplane in the very high part of the sky, this bomb is very dangerous because of the potential energy. So if you want to discuss about the danger of the bomb, you need to think about the where is the bomb. Okay, so enthalpy is almost the same thing. The internal energy is a kind of power of the bomb, and PV means the potential energy, like height times weight. So if you want to discuss about the reactivity of the system, we need to use this kind of thing, enthalpy. And by the use of the enthalpy, it's very easy to think about the chemical reaction because you can easily access the value of enthalpy by using the heat formation by the chemical reactions. I would like to explain that part by the use of this chemical reaction. The carbon solid can easily be react with the hydrogen gas, two molecules, to produce the methane with 74 kilojoule heat released. This heat can easily measured by calorimetry. So in this case, the delta H of this reaction equal to Q, that means minus 74 kilojoule. Why we need to use minus here? You can imagine this energy diagram. The y-axis is enthalpy, and this energy level is enthalpy of initial state, and this energy level is enthalpy of final state. And we see the heat released. That means the final state have lower energy. Then we observe the heat formation of the 74 kilojoule. So we need to add minus. This minus means the final state is lower than the initial state. Okay, and In this case, I mean, if you see the heat released, we say this reaction is exothermic reaction. And by the use of this, measurement, we can determine the heat of formation. I mean, standard enthalpy of formation equal to minus 74 kilojoule. Okay, so we say that the standard enthalpy of formation of methane is minus 74 kilojoule. This value is very useful in Hess's law. Okay, this is Hess's law. The change of the enthalpy of the chemical reaction is easily estimated by the use of the standard enthalpy of the formation. So this is very useful equation, so-called Hess's law. So the enthalpy change of the reaction equal to the sum of the standard heat of formation or standard enthalpy of formation of the product minus the sum of the standard enthalpy of the formation of the reactants. For example, we would like to practice to calculate the change of the enthalpy by the use of this reaction. The reactants is ammonia gas and oxygen, and the products are nitric oxide gas and liquid water. Okay, the 4 molecule of ammonia was react with 5 molecules of oxygen to produce 4 molecules of nitric oxide and 6 molecules of water. By the use of chemical reaction, we can calculate the heat which was obtained by this reaction by the use of standard enthalpy of the formation, which can easily find with the internet or something. Some textbook describe this kind of value as the appendix. And here is the equation to estimate the enthalpy change of the reaction. First, you need to sum up the heat of formation of the reactants. Okay? Products. Okay? So product is nitric oxide gas and water. And importantly, you should remember you need to add 4 and 6 because you use the 4 molecules. So the standard heat of the formation of NO gas, this is that value times 4, okay? And water value here. Importantly, water shows the minus, okay? And times 6 because we use the 6 molecules. And minus here, this one here, and this one here. And total amount of these values shows the minus 1,170 kilojoule. So the change of enthalpy of this reaction should be minus 1170 kilojoule. Then we can easily understand this reaction is exothermic. I mean, heat should be released. This is ammonia. Ammonia is sometimes used as the energetic carrier instead of the hydrogen or petrol. So it is very important that by the combustion of the ammonia, we can get a lot of heat like this. Okay, this is very important idea. And again, here you can see the change of the enthalpy is the change of the heat state of the state, these two states, reactants and product. And if you observe the delta H is negative, in that case we call this reaction as exothermic. And in that case, we can observe the heat released from the reactions. Sometimes the opposite type of reaction was observed. That means endothermic reaction. Delta H is positive. And in that case, the heat was not released. Instead of that, some cooling of the reaction system was observed. The change of enthalpy of the reaction was easily calculated by the use of the bond enthalpy as well. The bond enthalpy means the heat energy to break 1 molar of a bond in the gas phase. Okay? So, for example, the bond enthalpy of the CH bond can be determined by this kind of gas phase reaction. This is some molecule, okay, with the CH bond. And this CH bond can be cleaved by heat or something. In that case, we can determine the bond enthalpy. The important thing is that bond enthalpy should be always positive, okay? Because this is stable, this is not stable, okay? This is radical. This dot means the radical. H radical is extremely unstable state. So you need to think about the if you think the making a bond, in that case you use the bond energy always negative. I mean the release energy. By the use of this method, we can easily calculate the change of enthalpy of this chemical reaction, okay, by the use of the table of the bond energy. This is the table, okay? For example, the bond cleavage of the CC triple bond. We need to add the 835 kilojoule per mole for the bond cleavage. And HH single bond, we need to add 436 kilojoule to cleave the CC single bond. here, CH single bond here. And in the case of this chemical reaction, okay, we need to cleave one triple bond. And I mean, yes, one triple bond, okay, and one HH single bond. I mean, two molecules, so two HH single bond, okay. So one triple bond should be break, and two HH single bond should be break, and one CC single bond should be formed, make, and 4 CH single bond should be formed. Then we can calculate, this is the breaking bond. That means the positive, okay? And these are making bond, should be negative. So 1 times this value, 2 times this value should be positive, plus 1 times this value and 4 times this value should be negative. All value sum up, okay? The change of the entropy equal energy to break bonds, positive, and energy to make new bonds, negative. All these, values sum up to obtain minus 291 kilojoule per mole. So this reaction should be exothermic. Exothermic means the final state is lower energy, okay? So this is very important. So this reaction easily proceed because, this molecule have lower energetic state than these molecules, higher energetic state. Okay, so this is the final part of today's discussion. This is the practice, Please calculate the change of enthalpy of these two reactions. Hydrogen plus chlorine produce the hydrochloric acid. Hydrogen plus iodine to produce hydroiodic acid. Which reaction is more exothermic? This is a kind of, very important idea to understand the chemical reaction by the use of the change of enthalpy. You can use these values: HH single bond, Cl-Cl single bond, and II single bond. And HCl single bond and HI single bond. These bonds should be breaked, cleaved, and these bonds should be formed. So which is negative, which is positive, okay? And you can sum up all these values to evaluate the delta HCl and delta HI. This is the actually assignment of today. So please calculate these values and submit as an assignment of the today. And let's call it a day. Thank you very much for careful listening, and see you next week.